Hello, c'est Jeanmarc from MilliBox, and today we are talking about broadband capture. And when we are talking about broadband, we are talking about massively wide range. We are going from 14 gigahertz to 110 gigahertz in one shot, which is like unheard of, and we never tried before. So we are very happy to work for this with the Anritsu VectorStar ME7838. With its extender base. So basically we have a VNA, a full-fledged VNA which is very wide broadband from 70 kilohertz to 70 gigahertz from this head. But then with this extension and the extenders attached to it, you can reach 70 kilohertz to 110 gigahertz, if you can believe it, right? So for us, we are limited by the horn. We are using a very wideband horn from Eravant that allows us to do 11 dBi from 14 gigahertz to 110 gigahertz. So now with the power of the MilliBox setup attached to it, where we're using GIM06 with an MBX02. And then we have a very nice little setup that allows us to capture such extreme wideband from 14 gigahertz to 110 gigahertz. And because, as you know, our software captures the entire trace from the VNA, and for us the trace is complete. We can capture on the same plot, on the same sweep. We're capturing 14 gigahertz, 62 gigahertz, 110 gigahertz. I mean, as many points as you like. We could shoot for like 2,000 radiation patterns in one shot and in one go with such a large bandwidth. So that's pretty extreme, but that shows some usage that can be done with a MilliBox setup. And if you're lucky enough to get an Anritsu ME7838. Now, and that's different from other sweep that we showed before. 110, that's not the first time we did it. We had a video recently with the W-band, and then we did the D-band, and then we showed last year a nice setup in J-band at 330 gigahertz. That's fine. But it's always limited in range, for this band, on this band, or this band. Like you pick with the extender set, so you have a head that's more limited, like 20 gigahertz, and then you have extenders. You can move that spectrum, multiply that spectrum if you want to have like higher frequencies. But then you lose the lower frequency. That's when this setup comes handy, when you have like such a massive wide spectrum that you can use in one plot. If you're a lab with different students that have different projects at different frequency, this is a Swiss knife with all the possibilities out there. So that's one way of looking at it. So when we look at it a little bit closer now, we can see we have the head and the extender base. So you see there are like a lot of connection between the two to make that range expansion. And then we are wiring, these extenders head come with their heatsink here, and then they're attached to port 1 and port 2, and we have one here. So this one we attach the horn directly to the extender head, and then we wire straight. But we had to reach on the other side, and then we are a little bit limited in our setup with the cables that we got. And then here we have the extender head below the GIM06 positioner. And what we did instead is that we run a 1 millimeter coax also from Eravant that we are looping to that antenna, horn antenna, in 1 millimeter antenna, and that antenna that is the same as both sides, that can do 14 gigahertz to 110 gigahertz. So that's how we completed our setup. Yeah, so now we are taking control of the setup with the MilliBox software. So we are going to do a 3D radiation pattern. So we'll do heat map, and then -40 to +40 in azimuth, -40 to +40 in elevation, and then we do 4 degrees of step size in both azimuth and elevation. And here we are going to monitor the plot at 62 gigahertz. And let's get going. We're proceeding, and then we're going to update the real-time monitor, right? So that's where we're at. Okay, so what's happening here is that we are proceeding in a zigzag pattern in a stop-and-go mode, where we are covering the entire -40 to +40 degree in both azimuth and elevation. And we are capturing the entire trace of that massive bandwidth that we have. So we're going from 14 gigahertz to 110 gigahertz, and we have 97 radiation pattern in points in that trace. So basically we are collecting 97 radiation pattern, which is pretty much every gigahertz from 14 to 110. Every gigahertz we're going to have a new radiation pattern in that plot, and that plot is going to last less than 8 minutes, and we're going to have 97 radiation pattern. I'm repeating, but 97 radiation pattern from 14 gigahertz to 110, and every gigahertz we are collecting the data. So that's a huge amount of data that we're collecting with this setup. Let's watch. So while we are doing that, I'd like to check on the so this is actually the plot that we are collecting. You can see the data start with the target V and the actual V, the target H and the actual H, and then here we have the 14 gigahertz, 15 gigahertz, 16 gigahertz, 17 gigahertz, like I mentioned earlier. Those are each of the radiation pattern that we're collecting, and then we're going all the way up to 110. So that's funny if you think about it. That's a massive amount of bandwidth that we're covering with this particular setup. So it's very nice to see it in progress. So we're nearing the end of the sweeps. That's it. Okay, we're done. And one more line, and we'll be done. So was no issue during the collection. There's a little bit of odd shape, but that's the way this antenna is. So there's no worries there. Also, the gain is not that high. I mean, it's 11 dBi. So now, when we close it, then we do the rendering in 3D. And the thing is that we can always play back the data, and then so we go a 3D radiation pattern, and then we have 0, and then we do 0 to get the min max or what. So here we have from the same capture, we're just presenting what we have at 14 gigahertz, see? And then we close it and we do the rendering at 62, which is halfway. of the same plot, the same capture, and this is how it looks at 110. So very different shape, all from the exact same capture, the exact same run. Okay, so that's impressive. And I could plot any of the 97 radiation pattern that we collected, that we just collected in the last 8 minutes. Now, how is it in terms of correlation? That's what we are going to see now with the data from the manufacturer. See if we're somewhat the matching data. So we'll do minus 90 to plus 90. Step size we'll do 1 degree. And then, so we'll monitor at 62. No. So here we're doing we're doing the collection. This is what the datasheet from Eravant is telling us at 62. So just from the azimuth to azimuth comparison, I can even think that our sweep looks even better than the one that they have in the datasheet. We are seeing clearly the accentuation of the lobe, at 30 plus 30 degree, minus 30 degree, where we have that. So the important aspect here, for example, at minus 90 degree, we are at minus 20 dB. Then when we move at 60, we are crossing the minus 10 on both sides, and then we reach the 0 dB at 0 degree at the center of the both side of the lobe. So that match on both sides, even though, like I said, it looks like our capture looks a lot smoother and has many more points than they had for their measurement or their simulation. At this point, so we finished our capture. Now we're going to see what it does for other frequencies. So let me close this one, and we'll do a polar plot for HV sweep, so D. Okay, we do that, and D. Enter, then we do 0 for latest plot, and then here we can do 0 as well, and then we'll have the mean max. So here we have 14. Let's see what. So here we're seeing at 14 gigahertz. So it's really minus 90. That's where we are at minus 10 dB, and then we're going up. It's very omni, and there's a dent here, minus 75, but we can recognize some patterns. Then when we close this one, we go back to the one we just saw at 62. We already studied that one a little bit. And then we close this one. Now we're going to go to 110. So same plot. You see here those plots are very different in nature from from the 14 gigahertz, 62 and 110. They're so far away in frequency, and you see how the antenna is responding completely differently to the stimuli. So I mean, that's where we are at in the first glance at the correlation between what we measure with this setup behind me and what the manufacturer is telling us about their antenna. So we're pretty happy with the result. Of course, we would have to do a lot more analysis to conclude on the correlation. But that was a very interesting experiment to go through that. So as you could see, that's pretty massive. That's pretty original. I don't think it's necessarily for everyone. I mean, usually people are pretty much working in their own spectrum and for their application. But sometimes it's good when you have a lab with multiple users that have different requirements. That could be one way of getting there with this kind of setup. So if you have any question about this, I mean, first we're going to show it at IMS 2026 in Boston. We're going to show exactly this setup. So if you want to stop by, we're in booth 13075 on the floor in Boston for IMS 2026. So if you want to stop by, say hi, we'd be pleased to meet with you. And otherwise, you can always contact me and ask me any question about this setup. And if you want to know more, don't hesitate to contact us. Thank you. Talk to you later.